Okay, so today's objectives, we're going to describe viscosity, calculate friction force in a fluid flow, and actually, why don't we add one more? Let's describe a falling ball viscometer. So let's just write a little definition. What's that?
I read quantitative as quantity.
Oh. Oops. I'm going to give you some numbers here.
But those are Pascal seconds?
Yep, Pascal times seconds. Yep. So another unit. Another thing you should be aware of. That can be broken down. Anybody know what the unit of a Pascal is? The two other variables?
Or some force over some area.
Yep. So give me the unit of force. Here, Newton per meter squared. Yeah. So Newton over meter squared times seconds. You can break down the Newton more to keep going. I think. I'll have to double check, but I think it maybe becomes meter squared over seconds. Break it all the way down. But yeah, you'll see a whole bunch of different kind of combination of these. You just kind of have to watch out. So here, air is really, there's really low internal friction through air. The number is 1.83 e to the negative 5. So that's times 10 to the minus 5. That's what the E stands for. And then water is 1 e to the minus 3, shampoo 100, and honey is 1,000. So look how compared air to honey. That's so much, right? That's why it's so hard if you want to ever swim through honey.
Imagine breathing honey.
We're trying to breathe it. Yeah, it doesn't work too well. All right, so just remember, viscosity is an indication of how much internal friction is present. So how do we figure out what the actual friction force is? Well, let's take this, for example. Let's look at two parallel plates. So between the plates, we have a liquid layer, which is this red layer. We're doing a combination of 2D and 3D. So the bottom plate is fixed, it's not moving, but the top plate is moving to the right. And let's throw a coordinate system on here. And at the top plate, the liquid sticks to the surface. This top plate is moving to the right. The fluid sticks to the bottom. And we have between there internal friction, which is a viscosity force. What is the velocity of the liquid then if it sticks to the bottom of that top surface? Yes, it's got to be this velocity here. Okay, so the liquid up there is moving at that speed right there, v, which we're going to call u. Anybody want to know why it's called u? That's how we indicate in the x direction how velocity is moving. Okay. What about the velocity down here?
0. It's fixed.
It's fixed. The liquid sticks to the surface. So the velocity of the liquid is 0 because it has to stick. That's the fundamental rules of fluid mechanics. Is it liquid fluid sticks to the surfaces. So what does that look like on a graph if you plotted, let's call this distance between the two plates L. If I plotted V of the liquid layer versus Y, where would it be 0?
Y equals 0.
Yep. And what about at L? U. Yes. Yep. Which is up here, right?
It wouldn't be linear, would it?
It actually is in this case. It is. Yep. Yep. Experiments show that this type is linear. Yep. You get a linear relationship. So the liquid sticks here at the surface, and it's got going a velocity of u. At the very bottom, it's 0. And we have this linear profile right here. Okay? That's what actually happens in these cases. All right? So there's some sort of linear gradient resulting here. How would you find an equation of u with respect to y? Tell me, how would you find that equation of that line? What would you do?
Well, first, the slope.
You find the slope, and then also the y-intercept. Yep. So what's the general equation to find a linear line? Y equals mx plus b. Okay. What's the y-intercept? 0. So really, it's just the slope times y. How do you find the slope? Say that again. Rise over run. Yep. So it's
U over L.
say that again.
U over L.
Yeah, we could do that. Yep. So it's u minus what? 0. And L minus 0. That's cool, right?
And then if the bottom plate was moving, would be where you want your y-intercept.
If the bottom plate was moving, it becomes a little trickier. We're not going to cover that yet.
Okay.
So you kind of visualized with a sketch. We'll go back to sketches because they're important, right? And you said, we kind of know that the fluid sticks on surfaces. And if we plot this, we get this kind of graph. And then we can actually figure out what the velocity is in between. Okay? What is a slope in calculus? A derivative. Yep. Okay? So that's what it is, right? Okay. Why do we get this kind of profile? Anybody want to tell me why you think we get a linear, even if it isn't linear, but why do we go from 0 to velocity of v or u? Because of friction, yes, thank you. In reality, if you want to think about it, we can think of this layer as individual like ice cubes, right? Or molecules. The ones at the bottom, the very bottom, are touching and they're going at 0, right? And then the next layer up, that next box, they're going a little faster. Why? Why are they moving a little bit? It's fixed at the bottom, but then the top one's fixed. So the top one's, is moving to the right, and they're sticking to it. So it grabs the ones below to kind of keep coming with them. But eventually will approach 0. Okay, that's why you get that shape, because these molecules are all kind of touching each other and trying to force one to go one way. We get that type of thing. Okay. Does that kind of make sense? It's just internal friction trying to resist it back. What do you think a pipe flow, what do you think the velocity in a pipe flow would look like? We're going to get to this later in the semester, but just give you a preview. Yeah.
Wouldn't the graph go up and continuously go back down? Because both the top and the bottom of the pipe are fixed, so the one molecule is going to get stuck at the top, not the bottom.
Yep. Exactly. Where's it going to be fastest? Fastest. In the middle, yes. Yep. So we will do this, and I'll show you the equations we use for it.
That reminds me of surface of water.
What's that?
That reminds me of the surface of water.
Surface of water?
Yeah.
Yeah? Good shape. So that would be the profile that we use. Actually, that's a laminar profile. We'll talk about that too. All right. There's a turbulent profile that's different. All right. And we'll talk all about that later. But as long as you understand viscosity, you're good. All right. I'm going to keep going. So what did I tell you was the friction force in physics that you use? It's fun, right? So it's U times M. We use a very similar now if you have a liquid layer and you have a box on that liquid layer and it's moving on these plates. We can figure out what the friction force is. So what I'm going to do is I'm going to draw that kind of two plates again, but I'm going to do it slightly different. So say I grab that plate now, and I'm pulling with a force Ft. Okay, so I'm pulling that top force. And it's moving at constant velocity. What does that mean for acceleration? 0. So when you sum forces on that plate equals 0. You see the blue arrows? That's the friction force. If it's going at constant speed, what does that friction force actually have to equal? Ft, yeah, that force that we're pulling, okay? All right, so that's pretty cool, just to remind some stuff. All right, let me do a purple color. Oh, scroll up a little bit. You see that? If we go down a little distance, we call that delta Y. And if I go from that left black dot to the right black dot, we moved how far? Delta U. So I wrote area up there. So this new friction force is a function of a few things. It's a function of area. It's a function of this du dy, and of a constant called your dynamic viscosity. Okay, so let me write the equation now, and we'll go through it. And let's just kind of say friction force. We can call it that, which will equal Ft is mu times A times du over dy. So this friction force is a function of mu, which is your dynamic viscosity, your area, and what is that? Du dy. The slope. Okay. So this new friction force depends on how that velocity trend looks like. Bottom line, when you sum forces now, if you have a liquid layer, this is your new friction force right here. As long as you know your dynamic viscosity. Anybody know where you can find that? Books. Back of the book. You just got to know the type of fluid, and it'll tell you. Also have to know the temperature, because it changes. Okay? As long as you know your area, which is the surface area underneath, and the slope of that velocity profile that's generated between them, you can find this new friction force. Right? They've done experiments on this, right? I mean, they pulled with a force, known force, and back calculated and found that these match. Okay. Yep, that's what du dy is the slope. Yep. So if I gave you a velocity profile, you can figure out the slope, right? Which is just a derivative. Kinematic viscosity. Okay, so we have dynamic viscosity, which is mu, which is the Greek letter that's used in the friction. But if we divide that by density, we found that it is kinematic viscosity. Okay. Sometimes when we get to Reynolds number, the equation becomes a lot easier if you can divide mu over density. You don't have to worry about it. Just go from 2 to 1 variable. Okay. And the last thing we want to talk about today is the falling ball viscometer. We drop a known ball with a diameter d. We can use the distance that we've marked and measure the time, how long it takes. We can then find the velocity that's moving it.
Would the density of the ball affect that as well?
Yes, I'm going to show you that, yes. Yep. So we can use that. So first off, tell me what happens if you drop a ball in a liquid or you jump out of an airplane. What's going to happen to your speed? Wait, say that again? Okay, so say we put it inside the fluid and we let it go. It'll increase, right? Yes, it gets to a terminal velocity, okay? And that's when the drag force is equal to the weight of your object. You're no longer accelerating, okay? So that reaches terminal velocity. So when we do this, it has to be far enough down where we measure. It has to be in its terminal state. Otherwise, it's still increasing and it doesn't. You can't find an average. Their velocity isn't going to be average. All right, well, we also have to do one last thing on this ball to figure out the equation. Here's the ball. Anybody want to guess what we have to do on it? Free body diagram. Tell me a force acting on this. Gravity. I'm going to call it W, which is weight. Other forces. I'm going to talk, would you say? Okay. Anytime you have an object in a fluid, there's no normal forces because it's not touching another solid object. Okay. All right.
Buoyancy.
What's that?
Buoyancy.
There is, yes. That's who said that. Someone said it over here. I don't know. You did? Okay. Buoyancy force. Anybody want to know which way? We haven't covered that yet, but which way does that act? Up. Yep.
It's as if it were.
We'll talk about buoyancy force later. And then what's the last one? Which is what? Yeah, friction. Which is a drag force, okay? We call actually this is kind of its aerodynamics or hydrodynamics. It's a drag force, FD. So if we now do Newton's second law on this, we can use forces acting on this ball, and we're going to assume that it's no longer accelerating because it reached terminal velocity. We can plug those forces back in, and we can figure out how to find the viscosity. All right? Now, you don't know all these equations yet, which is fine. But I wanted to show you where this comes from. After we cover buoyancy force, you'll be able to now plug in what buoyancy force is. You want to take those three forces, plug in what they are. You can look online or I can help you to get to that. All right. So the buoyancy force, basically, we'll go through that later on. Okay. The drag force has your dynamic viscosity in there, and your weight has your mass and drag. And then you can rearrange those to find your actual dynamic viscosity. These is of the fluid and the solid, okay? So this is your gamma of the fluid, and then the other one's gamma of the ball, so S. This is your diameter of the ball. This is your velocity, which is moving, okay? And we can use that, your last question, we're going to use fine. Okay? Questions? Yes?
What's the sub S? The sub F?
This F is gamma of the fluid, so the liquid. So it would be here if it's water, water. And this is your gamma of the ball. Okay? And you remember what gamma was? You're not sure what you do. This is what I would do if I were you. Yeah, specific weight, right? What's that equation? Yep. So this is rho times g of the ball, so density of the ball. And this is rho times g of the fluid, so density of the water or whatever.